Hi everyone, by the way, my name is Jeffrey Salazar, and my topic for today will be the waiting line models with finite calling populations. For the waiting line models introduced so far, the population of units or customers arriving for service has been considered to be unlimited. In technical terms, when no limit is placed on how many units may seek service, the model is said to have an infinite calling population. Under this assumption, the arrival rate A remain constant regardless of how many units are in the waiting line system. The assumption of an infinite calling population is made in most waiting line models. In other cases, the maximum numbers of units or customers that may seek service is assumed to be finite. In this situation, the arrival rate for the system changes depending on the number of units in the waiting line. And the waiting line model is said to have a finite calling population. The formulas for the operating characteristic of the previous waiting line models must be modified to account for the effect of the finite calling population. The finite calling population model discussed in this section is based on the following assumption. First is the arrival for each unit follow a Poisson probability distribution with arrival rate A. Second one is the service times follow an exponential probability distribution with service rate P. And the third one is the population of units that may seek service infinite. With a single server, the waiting line model is referred to as an MM1 model with a finite calling population. The arrival rate for the MM1 model with a finite calling population is defined in terms of how often each unit arrives or seeks service. This situation differs from that for previous waiting line models in which A denoted the arrival rate for the system with a finite calling population. The arrival rate for the system varies depending on the number of units in the system. Instead of adjusting for the changing system arrival rate, in the finite calling population model, indicates the arrival rate for each unit. Operating characteristic for the MM1 model with a finite calling population. The following formulas are used to determine the steady state operating characteristic for an MM1 model with a finite calling population, where lambda is equals to the arrival rate for each unit and mu is equals to the service rate and n is equals to the size of the population. The first formula is the probability that no units are in the system. So you can see there the first formula. The second one is the average number of units in the waiting line, where LQ is equals to n minus lambda plus mu over lambda, open parenthesis, 1 minus p0, close parenthesis. The third is the average number of units in the system, where L is equals to LQ plus open parenthesis 1 minus P0 close parenthesis. The fourth one is the average time a unit spent in the waiting line, where WQ is equals to LQ over open parenthesis N minus L close parenthesis lambda. Fifth is the average time a unit spent in the system, where W is equals to WQ plus 1 over mu. One of the primary application of the MM1 model with a finite calling population is referred to as the machine repair problem. In this problem, a group of machines is considered to be the finite population of customers that may request repair service. Whenever a machine breaks down, an arrival occurs in the sense that a new repair request is initiated. If another machine breaks down before repair works has been completed on the first machine, the second machine begins to form a waiting line for repair service. Additional breakdown by other machines will add to the length of the waiting line. The assumption of the first come first serve indicates that machines are repaired in order they break down. The MML model shows that one person or one server is available to perform repair service. To return the machine to operations, each machine with a breakdown must be repaired by the single server operations. This model is often applied by a computer maintenance department of various organizations. An example, the Colmere Manufacturing Company uses a group of 6 identical machines, each of which operates a machine of 20 hours between breakdowns. Thus, the arrival rate or request for repair service for each machine is lambda is equals to 1 over 20, or it is equal to 0.05 per hour. With randomly occurring breakdowns, the Poisson probability distribution is used to describe the machine breakdown arrival process. One person from the maintenance department provides a single server repair service for the 6 machines. The exponentially distribution service times have a mean or 2 hours per machine, or service rate of lambda is equals to 1 half is equal to 0.50 machines per hour. With lambda is equals to 0.05 and mu is equals to 0.50, we use equations through to compute the operating characteristic for this system. Note that the use of equation makes the computation involved somewhat cumbersome. Confirm for yourself that the equation provides the value of P 0 is equal to 0.4845. The computation for the other operating characteristic are LQ is equals to 6 minus open parenthesis 0.05 plus 0.50 over 0.05 close parenthesis open parenthesis 1 minus 0.4845 close parenthesis is equals to 0.3297 machines. L is equals to 0.3295 plus open parenthesis 1 minus 0.4845 close parenthesis is equal to 0.8451 machines, where WQ is equals to 3295 over 6 open parenthesis 6 minus 0.845 close parenthesis 0.50 is equals to 1.279 hours, where W is equals to 1.279 plus 1 over 0.50 is equals to 3.279 hours, while PW is equals to 1 minus P0 is equals to 1 minus 0.4845, it would be 0.4155. So basically, you are just using those given and use the formula that I provide you earlier, this one. And that would be all. Thank you.